So for our second talk, we're very happy to have Petronela Radu from University of Nebraska-Lincoln, and she's going to talk to us about non-local frameworks. Floor is yours. Thanks.
Thank you so much, Trevor, for inviting me. Thank you all for being here at this talk. So I have to say that I've given this talk or very close versions of this talk a few times before. So this means hopefully that I took all the typos out, but we'll see. So I have become very interested in non-local theories and non-local models some years ago, where I was talking with a colleague in mechanical engineering at UNL, Florin Bobaru is his name. And he was showing me the simulations obtained with this new theory of peridynamics, simulations of dynamic fracture. This is a very complex phenomena, and the simulations match the experiment very, very well. So it just seemed to me that we must pay attention to some other methods of modeling things. So I started getting interested in it, and it turns out the mathematical theory, so this is back in 2008 or so, peridynamics was introduced in 2000, but the mathematical theory was largely undeveloped for many of these problems. So it seemed like a good time to jump into it. And even today in 2023, actually, it's not too late because there are many, many problems that are still open. And some of them I think are accessible. Some are really complex, but hoping for a large audience here with graduate students. If you get your pencils and paper ready, you can get some maybe projects on your to-do list for the future. So my talk has aspects in, as I say here, analytical, geometrical, and applied. And another belief that I have besides that hopefully we do mathematics that is somehow relevant to physical applications is that I think a lot of these aspects actually are very important to see together. A lot of times what we see analytically informs what we see out there in the with the phenomena. Geometric features can inform us. So I will try to pay attention to all of this. There's a long list of collaborators that I am very grateful to have had over the years. But more recently, this is the set of graduate students, undergraduate students, a couple of postdocs, and we have a couple of graduate students that left last May, and we're finishing up some projects with them, as well as collaborators outside UNL. And we have some other ongoing projects, but we are not far enough to announce results yet. So maybe next year I'll add them to the list. Hopefully we'll have something to report by then. So I'm not sure about everyone's interest in the audience. I'm sure it'd be very nice to be there with you and kind of talk more in person, hear what everyone is doing. But I have this slide talking about applicability of non-local. And I gave you the little introduction, what got me into non-local, this theory of peridynamics that was introduced in 2000. And it turns out it's not the only place where non-local frameworks have been introduced successfully. And by success, we usually try to see that they predict very well phenomena, and they predict accurately. For example, in the theory of peridynamics, we have a unified system. So you don't need any ad hoc methods that sometimes are used in engineering to kind of make the problem go the right way. With this theory of peridynamics, you basically let the problem go and the problem will tell you what the solution is. As Florin Bobaru mentions often, the solution is part of the outcome of the problem. So that's a feature that we like, but there are other fields besides dynamic fracture. They have benefited from non-local models, image processing, diffusion, phase separation, and very recently, the last 2 or 3 years, machine learning. They are introducing now non-locality and in different ways. I will see if I have time, I may say a few words about it. We have a project ongoing there as well. But mathematically, they are very interesting. The non-local theory is not only for the models that are set themselves in that framework, but a lot of times the methods that they give can help us even in sort of classical theories. And I put here as the last bullet the study of Sobolev functions and functionals, which if you look carefully at the paper, it's got a lot of ideas that have now been adopted in non-local frameworks. So the main thing that I hope you take away from today's talk is that nonlocal systems with appropriate kernels can deal with solutions that have very little, including L2 regularity. So you'll take these nonlocal derivatives, you'll study physical processes, and the solutions don't need anything else except integrability. So this ability to handle discontinuities is a key feature and key advantage why they are of so much interest in many scientific fields. But also nonlocal frameworks, they contain the theory of fractional derivatives, which is now over a century old, and a lot has been known about that. Somehow the theories are now getting quite a bit more traction, and that's because they are now extended to look at new concepts. For example, nonlocal curvature, that I will talk a little bit towards the end of my talk today. So I'll spend a few minutes talking about local versus non-local models. So when I use the word local, I mean to say that we use more differential, classical derivatives. Whereas for a non-local, we will use integral operators, often to approximate or to model the same process. So I can think of diffusion, I can use a local diffusion where I have the classical Laplacian, where I can have a non-local diffusion where I use a non-local Laplacian. In local models, and as I'm going to show you in a little bit, we usually capture depth of information, if you wish, given by the order of a derivative. A non-local model will capture the breadth, but since for many processes you need sort of a higher order derivative, what you may do is adjust your scaling or adjust the integrand that you take inside that integral. There are now non-local operators that mimic the Laplacian that are doubly non-local. In fact, there are several of them. So that doesn't mean that I'm approximating the biharmonic. In fact, we have the opposite situation, that there is a one integral operator that approximates the biharmonic. The only thing that changes is the integrand. In the local model, we capture the point or the local behavior. In the non-local model, we capture collective behavior, and I'll speak more to that. Mathematically, so I come from the world of nonlinear wave equations. So finite speed of propagation was something that we used in some papers when it was very important. Non-local models, if you integrate, basically you look at the evolution processes, you see this infinite speed of propagation. And although numerically engineers say, no, there is finite speed of propagation in these processes, at the mathematical level, that's not true. So there are some approximate results, and if I have time, I can tell you about that, but it is not quite the same. And if we come to modeling, the local models are preferred now for hydrodynamics. We just heard the talk in this field, conservation laws. Non-local models are now predominant in dynamic fraction, non-local diffusion, and I think image processing, although I'm not an expert. So I just have seen a lot of papers, and they seem to, these non-local models seem to do a very good job. Okay, so here's a little schematic of explaining this breadth versus depth. So in the non-local model, in the local model, let's just take a classical derivative, difference quotient, the limit. So you're trying to get better and better information as you get to a point X, and this limiting behavior is here captured with the derivative, the limiting behavior of this difference quotient. So in contrast, if I look at the non-local model, I take all the information that's nearby. So in the local model, I basically forget. As I get closer and closer to X, what happened behind me is irrelevant. But in the non-local model, we add everything up. So everything counts. Interestingly enough, there is a fundamental theorem of calculus that can connect two values in the local model. So in some sense, I can trace my way back if I have the derivative, but in the non-local model, if I give two values, it's not as clear of a result. One of our postdocs, Javier Cuerto Garcia, he may be in the room, I'm not sure. He has a theory that resembles this fundamental theorem of calculus, but there are some differences. Okay, so the other thing that should be mentioned is one can go from no locality to locality by localizing. And I'm very interested in this in particular. I did not mention earlier, but I'm interested to see how the non-local models approximate the local models. This is a central theme in many of our research projects, in fact. And you know, what they call the sifting theorem sometimes in the ordinary differential equations, right? I can localize, you know, Dirac mass will help me do that. So in some sense, a non-local operator, what it does is basically, we take some sort of approximation to this Dirac mass or derivatives of Dirac mass to get approximations of classical derivatives. All right, so these non-local problems are very important in many physical phenomena and complex phenomena. So in some sense, it seems that they could be the right tools when we have several phenomena happening at the same time. So here we have, for example, dynamic fracture. And by now there are quite a few papers that look just at asphalt breaking and having it modeled with a theory of peridynamics. And you can add to that set of equations diffusion or other dynamics that you want to have. And interestingly enough, you can combine. So you can have one set of equations in a non-local theory, the other one in the local theory. Even more interestingly, you can have this coupling, or on one part of the domain, you can have non-local, the other one would be local. And why would you do that? Well, it turns out that for all its advantages, non-local theories are more expensive in simulations, right? You have that integral operator. There are some other things that should be said there, but largely, you know, speaking, that seems to be the rule, that integration costs more. So then you try to use the most efficient model in the region where you don't expect a lot of interesting behavior, but if you expect somewhere to be a fracture developing, you may want to move to non-local. All right, so I will go a little bit over some of the theories in non-local. And to start with the theory, we have to define our non-local operators. And for example, even for non-local gradients, I would say the basic ones, there are many, in fact, infinitely many formulations, because each of these formulations, for each of these formulation, not only you have a structure, but in that structure, you can change the kernel. So this is very much in contrast with the local theory, or, you know, give me the derivative and that's the derivative. Maybe I take it in the weak sense. Okay, so here's another way. Maybe I'll take some coefficients, but in non-local, basically every time you change your kernel of interaction, every time you obtain a new operator. But not only that, I can define the derivative in many, many different ways. So every time I do that, we can come up with a new framework, and I'm going to talk about two such frameworks today, which has advantages and disadvantages. So I can have, for example, integration by parts work out very nicely, but maybe I cannot integrate explicitly, so I cannot have a fundamental theorem of calculus to go back. The Poincare inequalities, this is one of the first things that we try to develop, and Helmholtz decompositions. And I'm going to try to talk about a couple of results in Helmholtz-Hodge decompositions. We have another one in progress right now. And there are questions like non-local compensating compactness, although that seems to belong more to the, depending on which version you speak, that would belong more to the theory of non-local gradients, where you have a highly singular kernel. All right, so let's talk about gradients. So here's one form of a gradient. So you integrate over the space differences in the values of u. So I have u of y minus u of x. So I'm looking at neighbors y around point x. Now this neighbors y can go all the way to infinity, or I may want to restrict this to some small domain around x. And then we're going to weigh this values of the difference by a kernel. And usually for physical reasons, this kernel may depend inverse proportionally on the distance between y and x. So then I have 1 over y minus x to some power. But maybe there's a different way to consider this, where I have some other interactions, or I can even have a kernel that depends on u, in which case this could become a nonlinear problem, right? Because I would have a u in the kernel and then another u in this difference of values. The problems that we have focused on so far have a kernel k here that's integrable in L1. So if you drop this u out, you can look at this problem and see it as a convolution. So this is one possibility. And in that case, you can show easily that all I need for u is integrability, right? Because if this is integrable, then I can show that this integral is well defined. the one comment that I want to make sure I mention here, I kind of said it earlier too, is that if this kernel has finite support, so if I'm looking only in a ball around X, then for numerical simulations, basically I'm going to end up with a sparse matrix, and the width on the diagonal would depend on the horizon, what we call this size of interaction. What we would like to see is that as this horizon shrinks to 0, we basically are localizing the problem, so we're approaching a classical problem. And this is important for many reasons. We want to see some sort of compatibility with classical problems, which we know perform very well in regular situations, or the phenomena are nice, but it's also important to know for those coupling problems that I mentioned. So what if I want to couple a non-local region with a region where I use non-local with a region where I use local formulations? Then it's important to know what to expect. Based on, let me start with non-local divergence. So I can start with the expression for a non-local divergence, and I'm going to just focus on this case where psi is a scalar function, and so this is a framework that was introduced by Du, Gansberger, Lehouk, and Zhao. And if I have the values of psi at the x, y, and yx, then I weigh them against the kernel alpha. Note that here I have so-called two-point functions. So in this case, I take the divergence of a two-point function in order to get a one-point output out of this interaction. You can set this up with a kernel alpha that's symmetric or anti-symmetric, and all you have to do is to kind of change the signs here. So in this case, if alpha is anti-symmetric, you have a plus sign. If you take alpha to be symmetric, you need to adjust and have a minus sign. And then the adjoint operator with respect to L2 duality then will be this two-point operator. So now you give me a function that takes 1 point as input, but the gradient will be a two-point operator. So this is a little bit different than what we're expecting, but with this formulation, you can define a non-local Laplacian. And this is what I call the classical non-local Laplacian, is the expression that's most common in the literature, where the Laplacian being sort of a second-order differential operator is non-local, but it's simply non-local. I have only one integral, not two of them, right? However, the order, if you wish, of how deep the process is given by how many powers of alpha I have here, in some sense. So it's alpha squared corresponds to two derivatives, and if I were to integrate against alpha, it would be sort of a one derivative. But you have to be very careful with this integration by parts, because, for example, for this Laplacian, the two-point gradient, which has no integral, it's adjoint. So they're sort of algebraic, but also calculus aspects that we have to take into account. But we can associate to that gradient the divergence I introduced previously, and this Laplacian, we can associate a curl and an adjoint curl operator. And with this framework, one can show that a lot of the theorems that we know from calculus still hold. I'm going to focus on the last two here, that the curl of the gradient is 0. This one, third and fourth, and the divergence of the curl are 0. So these are equivalents of classical theorems. And when I first looked at them, I was hoping that there is a converse statement. If the divergence of a field is 0, then that field must be a curl. And if the curl of the field is 0, that must be a gradient. Turns out that that's not the case. So this was one of the things that sort of bothered me in some sense, that it doesn't capture quite the same thing that we had in the classical case. So in any case, with this theory, we're interested in obtaining a Helmholtz-Hodge decomposition. I'm going to skip over this because I imagine that many of the people in the audience are familiar with Helmholtz-Hodge decompositions, but they are extremely important in many applications. So in the simplest setting, you're trying to decompose a vector field into a divergence-free component and a curl-free component. This harmonic component that I have here usually goes away if you have a nice domain with appropriate boundary conditions. So,
Sorry, can I ask a quick question?
Oh yeah, of course.
So I'm just trying to understand the extent to which so that list of properties that you showed a slide ago with properties of the non-local curl and non-local divergence. I mean, this makes it conceivable that we can think of these as like as real analogs of the curl and divergence operators. But I'm wondering to what extent that's true, and specifically like. And I don't know if this question makes sense, but if you sort of take some horizon to 0, do you recover the classical curl and
yes, for all of them with rate delta squared, and if the function usually you need, so if I just talk about classical derivatives, you need 4 degrees of differentiability. So if you use in C4, you'll get a delta squared. So that's the one part. You can show convergence if you have less than that. So it's in the sense of Sobolev. Michael Foss has some results that shows that, in a weak sense, I can get convergence even if I'm in W2P, but then the convergence has no guaranteed order of convergence. So I just converge to 0 as delta goes to 0, but there's no power coming out. There's only one caveat here, the gradient. The gradient is that 2-point function is really just an algebraic structure. If I let that go to 0, like if I let the horizon go to 0, that becomes a quotient with 0 denominator. So it makes no sense. There's no integration, nothing there to save it. For all the other operators, you have a scaling factor in front, so that convergence holds. So all these theorems will hold true. So interestingly enough, you can obtain basically from non-local integration by parts, the classical integration by parts by going to 0, letting the horizon go to 0. So, there are interesting results like this, but not everything translates easily.
Sure. Thanks a lot.
Yeah. All right, so I'm going to go to, I want to say one more thing. So for this non-local theories, the other thing that we have to pay attention to is the horizon. So in particular, the impact on a horizon or the role of the horizon for boundary value problems. So let's say that I have here domain omega, I have some dynamics happening in the omega, let's say a diffusion type dynamic. Then what sort of boundary conditions do I need in order to get well-posedness? Well, you're going to need to set up a color around the domain, because if you think about it, I want to try to compute the Laplacians around the boundary. I will need all the points inside, but then I need all the values in here. So for this reason, the horizon of interaction will dictate the width of the boundary. Usually we take this to be uniform, but if you want to take a horizon that changes with X, then you're going to have to adjust this color as it goes. And I mentioned there was on a slide earlier, there's a Poincare inequality by Michael Foss, and he actually, you can have this canal of interaction be very general, and you get well-posedness. So with that Poincare inequality that he has. Okay, so we need a color. Not the simple boundary is not sufficient for this. There's some other interesting results I can talk about, like the dimension of the color can reduce if you adjust the kernel with appropriate weights, but I won't go into that right now. So here's one result of a Helmholtz-Hodge decomposition that I obtained with a group of women mathematicians in the University of Michigan a couple of years ago, and actually maybe it's more than a couple now. So you can decompose a 2-point vector field into a component that's a gradient structure, component that's a curl structure, and a harmonic piece. So first, I have a 2-point vector field. So U needs 2 inputs in order to give one value. The gradient, I told you, is that weighted algebraic difference. Like there is not no integral, no derivative, nothing on it. The curl is the adjoint curl. This one is defined at 2 points X and Y. The last component, this is interesting because you would expect this to go away under appropriate boundary conditions, and I take here to be 0 Dirichlet boundary conditions. However, it cannot be harmonic because I can't even apply the Laplacian that I showed you earlier to a 2-point function. The Laplacian would take a 1-point function. But we do show a similar property in this framework, and that is that the term H has to belong to the kernel of the divergence intersect with the kernel of the curl. So if you think in the classical case, that will give you, harmonic function, but here that cannot happen. And this composition, decomposition has all the properties that you expect in the classical case, in particular is orthogonal in L2 of omega cross omega. Now, we were very happy with the result because this was obtained on bounded domains. A couple of months earlier, Chang-Du and some of his collaborators had a result for 1-point functions, but they were on unbounded domains. So obtained with Fourier transform. So we tried to get something that where we can put boundary conditions. A year or two later, I was working on a project with an undergraduate, Andrew Haar, and we set up, trying to get this Helmholtz-Hodge decomposition to apply to one-point functions. We actually ended up setting up a new non-local theory by looking, just at convolutions. So we define a gradient to be just a convolution with a kernel. The kernel has appropriate scaling. And if this kernel is a vector valued function, basically for a scalar value function, you're going to get a vector, exactly like happens in the classical case. And you go on and you combine the convolution with appropriate algebraic properties, multiplication properties, and then so you have this cross convolution, this dot convolution, and each of them will give you the appropriate analytical operator. So I'll give a non-local curl, a non-local divergence. And then if I combine the divergence and the gradient, I'm going to get a doubly non-local operator. And this is a new type of Laplacian. So we showed that this, with this theorem, we have here a new framework that now applies to one-point function. So nothing here is a two-point function anymore. In particular, you recover as a sort of particular case the classical operators, because if you take these convolutions in the sense of distributions, then and you can take the kernel to be, for example, distribution valued, then you basically recover classical theories. You can also take these kernels to have different forms, singular kernels or non-integrable kernels, basically, strongly singular, and you can get fractional derivatives or operators that mimic fractional derivatives. And for example, there's a new class of operators that was introduced and studied by Jose Bellido and Javier Cueto Garcia, who is at UNL now, and we're working on obtaining some Helmholtz-Hodge decompositions for the new operators, and those have the stronger singularity and also have a finite horizon, which is important in applications. So another benefit of this theory is that you do have the converse of those two properties that I mentioned earlier. If the curl of the gradient is zero, then if the curl of a vector field is zero, then the vector field must be a gradient. If the divergence is zero, it must be a curl. And pretty much all the other properties that you expect in the classical case hold true. There are some things that have to be careful here. So if we are looking at solving these problems on bounded domains, this is not worked out yet. So pencils out, start writing open problems. But we do see convergence of the operators and all the stuff that we expect, including this non-local Helmholtz-Hodge decomposition, which was for us the beginning point. We were trying to get this result, and sort of along the way, we introduced a new framework for which the result held. All right, so I touched a little bit on boundary conditions, and I want to mention a couple of results that include boundary conditions. One we obtained with our collaborator Yu at Lehigh, and in this result we are solving a diffusion problem for non-local operators that have shrinking kernel, and what we're trying to see is that what is the limiting behavior of the solutions to the problem as the horizon goes to zero. So it has been known that if I consider non-local problems that basically approach from inside the classical problem, then I can get, I have a delta squared rate of convergence on the non-local operator converging to classical, and this delta squared rate of convergence will induce the same rate for the solutions that are associated with the problems. However, this is when basically I'm approaching the problem from inside. So let me mention a little bit a slightly different setup. So let's say I have the domain omega, because this is the one that we actually have in the real world. Now, an engineer comes and says, well, I read at the boundary a temperature of 5 degrees. Well, the instruments will not be able to give you a layer. So he cannot tell you inside that layer, what the temperature is at every point. So in some sense, it is up to the applied mathematician's job to set up some boundary conditions for which the non-local problem will be well posed, because if I don't have a color, the problem is not well posed. Remember that the operator sees outside, so I need to give some data on a width here. Okay, so the mathematician has to create this data on the boundary. Okay, so here's what the result says. If we try to extend, so let's say we said we know the classical solution. So this gray profile here is my classical solution. We take that classical solution, and if I use just a continuous function here with no other specification, then the solution to the non-local problem that has this red data on the boundary given is going to approach the solution to the classical problem, but it will approach it in a lower rate than if I were to take a linear extension to the known, to what I know to be the solution to the classical problem, or even a smooth one. For the smooth one, I have actually matching, I have the second order derivatives matching as well. So what this tells us is that when you set up this non-local problem, if you want good agreement with the classical problem, then you want to, on the boundary, you want to come as smooth as you can to approach the classical problem. Now, you may not know that. And if you don't know it, you don't know how well they match. If you don't know it, then the problem will still give you convergence, but not maybe the one that you want. So the better you do coming from the boundary, and this is the non-local boundary towards the classical solution, the higher the rate of convergence. I'm telling you basically a 1/3 of the theorem. The theorem has like 3 knobs that show how you can approximate the solutions to the non-local solutions to the classical problem with non-local problem based on these 3 knobs. What I have shown you here in the picture is one of the knobs, and it's a little bit of a simplified situation. But the full result is in this theorem, and I have one of the 3 parts basically in the inequality. So I can approach with a strong L2 norm, the classical solution U naught, with this non-local solutions U delta. And this rate of convergence will get better if my extension outside matches the classical solution better. All right, and you can get similar results for the evolution problems, and that means diffusion and wave or second order problems. So the one thing that we kind of bothered us is that the rates that we predicted theoretically were actually lower, and that's by delta to 1/2 than what the numerical rates show. So the numerical rates show to be a little better than the theoretical ones. And at this point, we have another open problem. Is it the case that the numerical simulations that are produced, and this, our collaborator, she did sort of a thorough job looking for bad cases. She had domains with corners, squares, she had circular, annular domains, but we are not able to find examples where the rates that we predicted theoretically were matched to show, okay, this is optimal. So the question is, have we now looked at enough numerical examples, where is there a way to produce a counterexample where maybe some functions with high oscillations or something will show that the theoretical rates we obtain are optimal? But speaking about data, we had some other work with one of our graduate students, Nicole Bukovsky, who is now at WPI, and our collaborator, Mike Parks, who was at Sandia, now he's at Oak Ridge. In this work, we showed sensitivity analysis of solutions to non-local problems when you change boundary data, or you can change the kernel, or the forcing. And we've done it for some linear problems, but also for a set of nonlinear problems. And I think the work is interesting because it can show you what effect little alterations in boundary data, for example, in this case, can have on the solution. So it's probably hard to see in this picture, but I can come with boundary data, the 0 for a while and then 1, and each of those will produce a non-local solution that approximates, better or worse the classical one, depending if I take 1 for a longer time or 0 for a longer time, right? So I'm going to be far off if I start here at 1. But basically, the sensitivity analysis shows that, little alterations in boundary data source or even the kernel can impact the non-local solutions. And also obtain the rate at which this happens. I should say in some specific L2 norms, we are not able to obtain them in as much of a generality as we are hoping. And we studied also some other diffusion problems even in the nonlinear context. And this generalized a linear problem that was done by Due and Mengesha for the biharmonic, we had a paper with Jeremy Trageser and Daniel Tundikov in 2017 that showed the same thing, that non-local solutions converge to classical ones. So sort of the lesson here is that these non-local problems have very rough solutions, L1, L2, but they converge strongly in L2 to classical solutions, which sometimes, have two strong derivatives. And we have shown some of those results even for nonlinear settings. We have a paper with a former student who's now at Carnegie Mellon. So now I'm going to shift gears just a little bit. I want to show you a couple of slides for Neumann type boundary conditions. So for Dirichlet, we have now almost 10 years of research. We've done quite a bit of work, or the field, not just our group, but the field has done quite a bit of work in understanding how Dirichlet problems work, rates of convergence, and so on. As I mentioned, we even have now results for nonlinear. But for Neumann boundary conditions, not for lack of trying, but the results have been much more difficult. So results in the literature usually would have some sort of ad hoc approach. So say, okay, I'm trying to approach with non-local problems this classical problem. The situation is much more complicated around the boundary. And I'm going to show you with the diagram why that is. So the boundary in Neumann, let's just think 1D, you have a derivative. This derivative in the non-local case, if you want to have integration by parts work and all this other results, ends up being a non-symmetric operator. And this creates quite a bit of difficulty. So in a paper that's, I say is about 2 weeks from being submitted, we have a new non-local operator, that Neumann operator that we introduced. And none of the structure is new. This is, in fact, this formulation was proposed by Chang, Du, Gansberger back in 2010 or so. What is new is the scaling in front. So note that even if I take a kernel that's homogeneous, I have only interaction that depends on the distance between the 2 points. The Neumann operator is going to be heterogeneous in the sense it is going to depend on X. And this Neumann operator is going to have to be set again on every point on this thick color. So it's not enough to just take the usual boundary condition, but you need to have a thick color for similar reason as before. Now, there was no question, like take a function here. This problem was well posed. So this was shown many years ago. But what was not clear is that this problem would approximate the classical Neumann problem. There were some cases that were investigated. So if we do this sort of ad hoc approaches, this will work. But what we showed is basically, give any kernel alpha that is in L2, create this problem, this associated non-local Neumann problem. And what we proved is that the solutions will converge quadratically. There were some results that showed that the solution converged. Actually, it's about 2 years old now. Xiaochuan Tian, who's at San Diego, but not quadratic convergence. Interestingly enough, our operator, this non-local Neumann, so this is basically a non-local derivative, we call it. This converges only linearly to a Neumann derivative. However, the solutions to this associated problem will converge quadratically. And I won't go into the details, but the reason is that you integrate over gamma, your basically boundary term. And when you do that, you get another delta. So the solutions will get the delta squared that we're expecting. But along the way, a very interesting phenomena has happened. So we introduced a new concept of the point operator condensated convergence. And I mentioned here that I need to set this Neumann boundary condition at every point in the color. So the idea is that if I am at a point, I'm going to call it X nu here because I'm going to try to approach A. So if I'm at a point X nu in the color, as delta shrinks, so basically here, you can think that I'm being chased by a train or something. So as delta shrinks, I'm going to go faster towards A. So let's say that the endpoint here of the interval approaches A at the rate delta. Well, it turns out that if X nu approaches the point A faster than delta that comes behind, so let's say goes delta cubed, there are cases when we don't even get convergence of that Neumann non-local operator. So in fact, the limiting case is a rate delta squared. So at delta squared, we already lose convergence of that point. So we have, okay, let me see here. So we have basically pointwise convergence. But how is this pointwise convergence? Is x converges, so I have x nu, so that's a one scale basically, and I have delta convergence because the end point is shrinking, so that's a two scale convergence. Well, the two rates don't have to talk to each other. I do need this point x nu to converge faster because otherwise I'm left outside of the integral, and I need the non-local Neumann to see the interval because that's how it's defined, right? I'm defined here, so I can't be outside because at some point I'm going to see nothing, right? The rate of interaction is finite. However, if I go too fast, I will lose all rate of convergence. So somehow I have to go at a rate that is between delta and delta squared. And this is in 1D. I have the computations done in higher dimensions as well, and I think it's the same case in higher dimensions. But the paper is written up for one dimension because it turned out to be sufficiently complicated. So, so I have this two-scale convergence that shows that the non-local Neumann that we produced converges to, in the end, at a linear rate, assuming that this point x nu converges linearly with respect to delta. If you try to get faster, it's actually going to cost you and going to get the worse rate. And you cannot go slower than delta because you end up being outside of the interval, so convergence is lost again. So this is the definition. I won't go through it. This is the operated point condensate convergence, and you can, talk about much larger, different operators and stuff. And I probably will skip some of these things that I mentioned earlier. I told you we have convergence results for nonlinear problems. It turns out it's actually very difficult to deal with nonlinearity in this case because you lose compactness, you lose a lot of good properties. I thought that this is going to be like a 3-month project, and it ended up taking almost 2 years. The interaction between terms is very difficult, and we have obtained results where we have a lot of restrictions on the nonlinearity, and in that case we get a good rate of convergence, and then we have results where we relax those a little bit, not very much, but then we lose the rate of convergence. All we can tell is that yes, they will converge, but we can't tell at what rate anymore. So, and then as the previous talk was about conservation laws a little bit, we have so with my student Einvo, we have some results on nonlinear conservation laws and kind of similar problems where I try to see how fast do the solutions converge. And these are, we have the results that are in different scales. So we have a variety of regularity assumptions imposed on the input functions and also on this flux F. So different smoothness assumptions, we get different rates of convergence. With Olena Burkowska, we actually have a slightly different problem. She works at Oak Ridge, and Ein was her intern. Well, during the pandemic, was really virtual intern, but we have a diffusion problem. So to this non-local divergence, if you wish, we have a non-local diffusion term, and then we look at the interaction between the two non-local operators, which may have different kernels. So that's actually turns out to be interesting enough. But do I have 2 more minutes?
Oh, yeah, you have almost 10 more minutes if you want them.
Okay, I will try not to fill them all up so I can save some time for questions. I think I don't know, I can't see all the participants anymore. I think our postdoc Animesh was in the room. So I think that sometimes during seminars it's kind of cool to look at new problems. And here's a cool problem that's very, very difficult. So I'm going to talk a little bit about non-local curvature, but I will motivate it first with non-local perimeter. So here's kind of a simple setup. So let's say that we have an image. In this case, we have a square that we're trying to approximate with pixels, like you would. And I'm going to try to cover this with pixels that for which the resolution is increasing. So in this case, I will say that I have this little blocks which shrink in size. Well, we know that for a square of, if I have length 1, then these 2 sides will have length 2. If I try to measure with this pixel, so I look at the perimeter of the pixels and I'm trying to measure to get an approximation of the perimeter, I will never be able to do so because every time we decrease the resolution. So if I go with darker and darker colors here, it turns out that the perimeter doesn't shrink. In fact, it's always going to be a square root times the actual thing. And it doesn't matter how tiny I make these things, which is kind of incredulous. Like, if I get smaller, I should get closer to the actual one. And the answer is no. It's just simple geometry, right? It doesn't work this way. So one of the motivations is that, for example, you can introduce a concept of non-local perimeter, where if you shrink this cells, basically, that cover your domain, as you let the horizon go to 0, you will approach the actual perimeter. But the more interesting part for me is that the physics, the beautiful real world, which is very rarely smooth. So let's think that you try to define perimeter. If you look at the seashell or sea star, anything that you did for which you don't have a smooth boundary is going to be difficult and actually impossible if you try to use just classical tools to get the actual perimeter, right? So you have sets with that are very complex, disconnected with cusps and everything. So if you try to go to curvature, like in a sort of classical sense, you would expect 2 degrees of regularity, and that is very rarely given to us. So then we still need tools to kind of analyze the physics. So if the classical tools don't work, what can we do? So non-local perimeter and curvature problems have been introduced. There is by now quite a long list of analysts. They introduced them through the idea of fractional derivatives. But I happened to find this book by Rossi, where the non-local curvature was introduced through integrable kernels. So these are singular, biweekly singular kernels of interaction. So I can integrate them, which means that just as before, I don't even need continuity to define a non-local curvature. So what does it measure actually? So this can be explained to anyone, even a kindergarten child. So if I take a domain, and let's say I put a point on the boundary of the domain, I'm going to try to cover, I'm going to place a ball, I'm going to try to place a ball centered at X there. And I'm going to try to measure how much area is inside the domain minus the area outside. And I think I put I said the opposite. So it's a minus sign in there, right? So how much is inside minus how much is outside, but what I can see through my lens, right? So my lens has only this horizon, let's say delta. And this is non-local curvature, which means I can define it at this point. I can define it at this point. In fact, we can define non-local curvature inside the domain. I can even have the point inside. And of course, if it's fully inside or fully outside, this will become trivial. But you can see I can be very close to the boundary in some sense, and the exterior will have an influence on me. So I can actually see this. I call this sort of non-local curvature a way to measure how open the domain is to the exterior. So if I have like a finger-like domain, right, this is more close, the curvature will be high. But if I have something flat, it's almost, 0, taking the 2 areas, they'll cancel each other. So it seems to me that this is a more physical concept because, for example, transfer of mass, transfer of information goes from one region to another. It is in some sense dictated by how open, how much contact you have with the exterior. So to me, the curvature is becoming a little bit of a different concept with this new definition. And as it turns out, if you scale this appropriately and you have, for example, a boundary that is at least twice differentiable, you will approximate the classical curvature. And this is in Rossi's book. But the problem becomes extremely difficult. So you can have an undergraduate student and just try to compute non-local curvature for even very simple figures. Like this one, right? This is a polygonal contour, and it is very difficult to obtain a closed form for the non-local curvature, the actual computation to do this. But physically, it seems that it's a concept that we should understand and know, because how much, the difference of the 2 regions is would be important. But for the analysts in us, there are a series of questions. So here's the first one that we gave animation. He arrived at UNL a couple of years ago, and we thought it's going to take, like 6 months to work over this. And I think we're wrapping up the paper now. Basically, if we have this non-local curvature which is constant, must omega be a ball. So a couple of years ago, there were 2 papers or put out that show that if I have this kernel that is highly singular, then the answer is yes if the kernel of interaction has infinite support, and if it has finite support, then it's a union of balls that are situated at distance delta away from each other, right? Because once I don't see past delta, then another ball can form, and so on. But we are focused on the problem when the kernel was integrable. So by the time we finished our proof, it turns out there was some work by Bucur and Fragala who showed that this is the case even for integrable kernels. And they obtained for quite general sets, but we think that we are able now to generalize the results to actually very general balls, measurable, so you don't even need them to be open. Well, we also looked a little bit at the prescribed curvature problem. Can you get existence or maybe, you know, uniqueness? This is even for the classical case, this is a very difficult problem, but is there something that we can say if we try to solve the curvature is given by a function f, then what should domain look like? How, you know, do I have uniqueness, under what circumstances, and so on? And then what would the regularity be? There's a part that's actually not trivial that we have, that what it says that if we have actually a boundary which is continuous, the curvature will be continuous. And this is interesting in the sense that if you have, in the classical case, you know, you can have a continuous boundary, but, you know, the classical curvature may not even be well defined. So it shows in some sense the usefulness of the concept, but of course we'd like to go the other way. If I know something about the curvature, what can I say about the graph? All right, there are many more interesting problems that we could tell you about, but I think that the best part of nonlocal theories is that the multitude of problems and aspects that it opens itself up to, and there's so much to still be discovered. So I hope that my talk is especially useful to graduate students and more junior mathematicians, because I think there's a lot to do out there. And yeah, the nonlinearities that we encounter here somehow seem to be, a lot of times we don't know what to do because we don't have the methods. So I will thank you all for your attention, and I think I ran out of time, but thank you.